about regular expression matching using bit vector automata.
Okay, hi everyone. My name is Konstantinos Mamouras, and I will be presenting our work, regular expression matching using bit vector automata. This is joint work with Alexis, Glaunec, and Lingkun. So classical regular expressions are built from concatenation, nondeterministic choice, and Kleene star. And we know from Thomson that a classical regular expression, or regex as we say, can be translated into an epsilon NFA whose size is linear in the size of the regex. This is all very nice, but real-world regular expressions need more constructs than just the classical ones, including bounded repetition, also called counting, look-around assertions, and back references. In this work, we specifically focus on bounded repetition, which is known to not increase expressiveness, but makes regular expressions much more succinct. In fact, it is known that the smallest DFA that recognizes the regex dot star a dot n needs 2 to the n states. And an implication of that is that the smallest NFA that recognizes the same language needs at least n states. This is not just a theoretical curiosity. Bounded repetition can cause substantial performance degradation in existing regex engines. So you might be wondering, why do we care about all this? Well, regexes, and in particular regexes with bounded repetition, are widely used for extracting information from unstructured data. And the key computational problem that is relevant here is called regex matching, which amounts to finding occurrences of regular patterns in datasets. There are 2 main techniques for regex matching. One is based on backtracking search, and the other is based on automata simulation. The advantages of backtracking is that it's easy to implement, and it's also very easy to integrate advanced features like look around and back references. The main disadvantage is that backtracking has worst case complexity that is exponential in the length of the input text. So this is pretty bad. In fact, it has a name. It's called catastrophic backtracking. Now, for the case of automata-based regex engines, DFAs or NFAs are used, and there is an interesting trade-off here. DFAs require much more memory, but they're a lot faster to execute. NFAs, on the other hand, are much more memory efficient, but they can be pretty slow. Because of this trade-off, modern automata-based regex engines typically use a hybrid algorithm that combines both NFAs and DFAs. Now, most existing regex engines unfold bounded repetition before they can construct NFAs or DFAs. Unfortunately, this unfolding gives rise to NFAs of exponential size and therefore DFAs of doubly exponential size in the size of the regex. This means that the memory requirements can blow up, but also the throughput of matching can plummet. So, because of these issues, we are led to consider the classical model of non-deterministic counter automata, or NCAs, which are a natural succinct representation of regular patterns with bounded repetition. In fact, NCAs have already been considered in prior work. So we have recent work with collaborators on the design of a hardware accelerator for regex matching, which is directly inspired from the NCA model. There is also a paper from 2020 on the software regex engine CA. Here is the NCA for the regex dot star, sigma 1, followed by the repetition of sigma 2, sigma 3, sigma 4 from m to n times. The states Q3, Q4, and Q5 form the one and only loop of this NCA, where Q2 is the entry state of the loop and Q4 is the exit state. There are two kinds of states in the automaton. Some states don't have a counter. We also call these pure states. And some states have counter named X, and we call these counting states. A transition between counting states is annotated with three labels. The first one is a predicate sigma over the alphabet. This is also known as a character class. The second label is a guard, which is a predicate over the counter X. And the last label, which I call an action, is essentially an assignment to X using the previous value of X. Now look at the highlighted portion. This essentially says that to enter the loop, we set the counter to X. To repeat the loop, we check that X is less than N, and then we increment X by 1. And to exit the loop, we check that the value of the counter X lies between M and N. NCA simulation requires maintaining a configuration, which is a set of tokens of the form Q, I, where Q is a state and I is a counter value. If we fix a state Q, the set of all tokens whose first component is Q can be represented with a bit vector of size n. Let's call this V, where V of I is equal to 1 if and only if the token Q, I belongs to the configuration of the automaton. This gives rise to the concept of a non-deterministic bit vector automaton, which associates a bit vector to each state. Note that the NBVA has exactly the same topology as the corresponding NCA. The difference is that it manipulates bit vectors instead of counters. States are classified according to the size of their bit vectors. Now, a transition from a state of type M to a state of type N is annotated with a character class sigma as well as a bit vector action, which is a Boolean function from b to the m to b to the n. Also note that if we have a state with several incoming transitions, then the bit vectors from the incoming states are combined using the bitwise OR operation. Entering the loop corresponds to creating a bit vector which is 0 everywhere except for the lowest position where it's equal to 1. Repeating the loop amounts to shifting the bit vector by 1 position, and exiting the loop corresponds to checking that the bit vector has at least 1 bit equal to 1 from position M to position N. For the example that you see on the slide, naive NBVA simulation has time complexity theta of n per symbol, where n is the upper repetition bound. This is because of the complexity of copying bit vectors and performing the bitwise OR operation. So the question we want to answer now is whether it is possible to do better than this time-wise. So indeed we can, and we propose an algorithm for which time per symbol is independent of the repetition bound n. And the main idea behind this is a technique for the efficient manipulation of bit vectors. I will show the key ideas of the algorithm by example, and to simplify things a little bit, let us consider both the lower bound and the upper repetition bound to be equal to n. The algorithm will focus on what happens on the states of the loop, namely Q2, Q3, and Q4. The algorithm maintains 3 bit vectors, V2, V3, and V4, all of size n, where vi is the bit vector that belongs to the state qi. All of these bit vectors are initialized to 0. Now let's look at the function update, which describes what happens when the symbol A is consumed. Looking at the pseudocode, the first step is what I call a rotation of the bit vectors. So this is just moving the bit vectors along the arrows of the automaton. The next step is shifting V2 by 1 position. Then we check if the incoming edge carries a non-zero bit vector, and if so, we set the lowest position of V2 to 1. Then for every I from 2 to 4, we check whether the symbol A belongs to the character class sigma I. If not, we set Vi to 0. Finally, update returns the value of the bit vector V4 at position n. Let's discuss the time complexity of this procedure. Notice that the rotation of bit vectors can be done in constant time using pointers. Also notice that the update function uses several bit vector operations, including shifting a bit vector by 1 position, setting the lowest bit of a bit vector to 1, setting an entire bit vector to 0, and reading a specific bit from a vector. A key idea is that all these operations can be supported in constant time using a data structure that is essentially a resizable circular n-bit array. So more details on this can be found in the paper. The main theorem is that the repetition of sigma 1, sigma 2, up to sigma k from m to n times can be evaluated in any context with time complexity big O of k per symbol, which is independent of the repetition bounds. In fact, our efficient algorithm can be generalized to a broader class of regular expressions that cover the bounded repetition of a regex R, where R accepts only strings of some fixed length. We have implemented the BVA scan regex engine in Rust. BVA scan incorporates both our efficient algorithms for bounded repetition as well as several performance optimizations. In particular, it uses bit parallelism to speed up bit vector operations for NBVA simulation, and it also integrates efficient algorithms for string search, which is a very common but much easier special case of regex matching. You can see now on the slide the plots for 2 micro-benchmarks where we compare BVA scan against PCRE, RE2, and CA. We use 2 regular expressions that allow us to focus just on the performance of the algorithms. The main observation is that BVA scan has running time which is independent of the repetition bound k. PCRE and RE2, on the other hand, time out. Finally, notice that CA cannot support the second regex. We have also used several benchmarks that are representative of real application domains, including network intrusion detection, bioinformatics, spam detection, as well as malware and virus detection. Take a look at the plots at the bottom of the slide. If a point is below the diagonal, that means that our engine, BVA scan, is faster than the competing engine. We consider, as before, CA, PCRE, and RE2. So notice in these plots that BVA scan is faster than the competition in the vast majority of regular expressions. I'm just showing the results for Snort. The results are pretty similar for all the data sets that we have considered. Now, take a look at the table in the middle of the slide. The key thing to notice here is that the average speedup of BVA scan over other engines is at least 10x. You can find more experimental results in our paper. Now, I'd like to conclude with a summary of the main contributions of our work. We have introduced the new model of non-deterministic bit vector automata, which is a succinct automata model for regular patterns with bound repetition. We have proposed new NBVA-based algorithms for the efficient matching of regular expressions with bound repetition. The main result is that the time complexity of our algorithms is independent of the repetition bounds. We have also implemented the BVA scan regex engine, which incorporates the algorithms as well as several other useful performance optimizations. And finally, we have experimental results that show that BVA scan has good performance against PCRE, RE2, and CA over the workloads that we have considered. And with this, I'd like to conclude my talk. Thank you for your attention.
If you have a question, please step up to the microphone.
Hi. So my question is about, maybe I missed it, but you showed a model initially but with a counter, and then you switched to bit vector. So
that's right.
Why did you not use a counter model? Why did you need the bit vector?
We are using counters. They're just represented using bit vectors. And the reason behind that is that they can be manipulated efficiently.
But the integral counters, you think they cannot be manipulated efficiently?
Right. So let me go back.
Yep.
So you are talking about the relationship between the NCAs and the NBVAs.
You're disconnected already from the screen.
Oh, okay, I guess it does.
You can just say maybe, it's fine.
Yeah, so the idea is that a bit vector can compactly represent a set of different counter values. So these two are equivalent things. And algorithmically speaking, using bit vectors is advantageous, both because it allows us to describe the algorithm more effectively, but also because we can use bit parallelism. So this is a performance optimization on modern CPUs because we have registers that can manipulate many bits at the same time. So this representation allows us to do much more work using just a few operations of the CPU.
Okay.
Right, so it's both conceptually useful and also very useful for an efficient implementation on a CPU.
Okay, thank you.
All right, please join me in thanking the speaker.